So this week we will, as a kind of the Python part of this week, we will focus on learning the spatial data model and kind of how to create geometric objects using this Shapely module that I mentioned already earlier. So you will basically learn how to create points, lines, polygons, and these kind of things that are kind of the core elements in the vector world of GIS. And then there is the exercise for this week, where you kind of learn and practice to do those yourself. There are already the lesson videos from last year. You can take a look at them if you want. They should follow more or less the same structure as this one, but missing, of course, one of the things that is basically how to use these environments. So this here we have similar buttons as with the GeoPython. So we have the binder, and I could launch this one. So there's the student binder version, and then this full binder having exactly the same materials as written in here. Then there is this Cse Notebook. I could actually now launch that and introduce you to it, because it's now a bit different. So we updated the system a bit because we needed to have all the packages, GIS packages installed. So what you should, I don't want to destroy anything. So this might look a bit different than what you will have, but if you log into the CSE environment, you should have this GIS Jupyter Lab kind of environment, which is developed now for this course. And in a similar manner, you can just launch a new course or new instance of that Jupyter Lab, and it has 6 hours of lifetime, so it will destroy itself after that. But what is actually different now is that when you click this open in a browser button, it will first of all give you this password. You should click to copy password and proceed. And when you do that, what it will still ask you is that you just paste that password in here and you log in to the system. Why this is done is that now you don't anymore have temporary working space. You have permanent place for your files, and they will stay there. So if you do some for example, write some files and so on in here, they should be there available whenever you log in using your own university account. So there was some kind of progress done on that level. So whenever kind of, feeding that password and logging with your own account, that is what should happen. So even you basically, if you use this CSE notebooks, even if the 6 hours destroy mechanism activates and you have some unsaved work, it should, not unsaved, but if you haven't uploaded that to GitHub, it should still be there for you. I haven't tested that, but that's what I've been told, so I hope that is the case. But just to be sure, so I still recommend pushing and uploading your work all the time to GitHub. Yes, when you launch, so again there will be these notebooks for each lesson, and you can kind of start playing around with these. And I will now continue and start with the lesson 1, just to check that the binder. So why this year the CSE version of the instance might be even more lucrative option for you is that because there are many packages that are installed every time when this binder is starting, it might take actually much longer than before to get that environment working for you. So it might be kind of faster way, or should be faster, to actually use the CSC instances for doing the exercises and going through the materials. But let's continue with the materials. I might actually start from this view because it's easier to maybe see. So what we will now go through and learn is how to use Shapely and how to basically create different kind of geometric objects. This is might be a bit, well, boring, but this is something that you need to learn because, well, of course, as you are, most of you at least, are geographers, so points and lines and polygons are quite self-evident things. But still, these are kind of, now you need to know how to create those in Python and what kind of functionalities these objects has. So of course, as well, most of you understand, when doing GIS you have different kind of geometric features and objects. You have points, you have lines. In Python and in, well, many programming languages, when we are talking about lines, they are typically called line strings. And line strings are such that you have nodes and then you have like connecting lines between those lines, and they can be like this. You can have linear ring that is like starting and ending to the same node, and then, well, you might have multi-line string that is an object actually kind of constituted of many different lines. Maybe the typical thing, well, you might have multi-lines as well, but most often you have multi-polygons that might be. If you think about some archipelago, so you might have like different islands and they are bound together. So that's maybe a typical case in geospatial data, where you have kind of a bundled multiple different geometries together. And, well, polygons are of course one kind of key features or key geometric objects that are available. And, well, as in any polygon, you can have the kind of boundaries, but then you might have holes inside. So we will learn today how you can create polygons and how you can actually create a hole into that one. Typically, you don't need to create at least these kind of geometries, like pretty complicated, where you have like a polygon and you need to create holes. So typically you read some data in, and the kind of features have been digitized by someone else. But, well, at least you know how they can be done, and it's anyway important to understand that you have these kind of features in here. So so we will basically create points, lines, and polygons. Then what we will, well, maybe what we will also learn is that basically these basic features or spatial objects, so they have already a lot of features and functionalities in themselves. So typically when using some software and you, for example, want to calculate distance from this point to another point, you need to find some tool somewhere that you can actually use that and do the calculations. What we will see today is that actually you can do that by using not any tool. You can just use the functionalities of these objects themselves and calculate the distance from itself to another, and get information about how what is the length of the line, what is the area of a polygon, and so on. So these kind of basic things we can do directly with the spatial or the geometric objects. Good, but let's start going through. So now here I have the Jupyter Lab open, and let's see how we can actually create a point. So if you want to follow, you can use the binder version of the lesson, the student one, or then you can use the Cse Notebook, whatever fits you best. Can you see the screen on the back? Yeah, good. So, as said, so basically what we are going to use when creating these geometric objects is this package called Shapely. So that is a package that is pre-installed into this system. Typically when you use the Shapely package, so you don't actually want to import the whole package but some features of it. So we use this from Shapely.geometry. So this is kind of a submodule containing all the geometric objects that are available, and from this kind of submodule we want to import point. So this is kind of an object that we can use to create points in space. So import Shapely point object from Shapely module. And when I launch this, no module named Shapely. Well, this is great. Let's try this one. I will need to take a look at the binder version. It should be there, but some reason it's not. But here it should be. So if you follow, use the Cse Notebook version. So here this worked. So from here we can import point, but we can typically I want, at least I do, so that I import all different geometric objects at the same run. So by using and separating with comma, I say that import also line string and import also polygon, so that I have all these different objects now at my hand and I can actually start using them. So how do I create a point? It's pretty straightforward. So let's create a variable called point1. So we have 1 point in here, and the key of how to construct a point is to use this point object that we imported. So by calling this point, it actually, oops, not like this. No, I have forgotten it. Yes, I learned this. This is pretty neat. So if you press Shift and tabulator, you can get the documentation of any function or object that you have. So from this documentation we can see that how to use this point. So it takes some arguments in there, it has different attributes. So what should we actually pass into this point object is that it should have x, y and z kind of coordinates. So well, x is the x coordinate, so longitude, y is the y coordinate, latitude, and z is the height, if you have that information as well. So how we create a point is that we pass numbers into it. So this now basically takes a point at coordinate location 2.2, which is the x coordinate, and 4.2, which is the y coordinate. And if I launch this, what I should have is that I should have this kind of point in here. So when you call this point 1, what Jupyter Lab and Jupyter Notebooks is actually showing is this kind of point looking object when you do that and call it. If you print the point 1, you will actually see this kind of information. So this is kind of telling that you have point geometric objects at coordinates 2.2, 4.2. And this is a representation how GIOS, which is one of the underlying geospatial packages, that is actually Shapely is depending on this GIOS package, so which is written in C if I remember right. So this is kind of the way how the coordinates are and the point object is presented. But so just like that we were able to create a point. So just by adding some coordinates inside the parentheses we can create a point object. Let's create another one as well. So let's create point 2, and let's say that point 2 is again, it's a point, and let's give it coordinate 7.2 and minus 25.1. Let's also create a third point. So point 9.26 is the x coordinate and minus 2.456 is the y coordinate. By the way, typically or quite often you pass the coordinate information in latitude and longitude kind of projection using decimal degrees. Which one of these is latitude and which one of these is longitude? X and Y. So this point object always takes as a input values x coordinate and y coordinate. Can someone tell me which one is which? So is x latitude or longitude? We typically say lat long, but yes. So this can be a bit confusing, especially in the beginning when working with this Shapely, because it indeed takes x and y coordinates, but x is actually longitude and y is latitude. So it's kind of, as we say, that lat long coordinates, and that's kind of a typical way in the spoken language how we describe these decimal degrees. So it's kind of the other way around when passing those information in Shapely. So just that you know that when you create some kind of point map, that you know how it should look like, and if it's kind of upside down, or not upside down, but kind of 90 degrees off, it typically means that you have put those coordinates in wrong order. Yeah, so that's just a note. Let's create a three-dimensional point as an example one. So let's use the same point 3 as a basis, but if you want to put the kind of three-dimensional information here, you just add one coordinate in here. And now we have a set of points that we have created, and we can take a look what is the data type of point. So point type. So again, we can use the same Python functionalities that are available. So if you want to take a look what is the type of certain object or a certain thing, you can always use this type command, and you can pass the variable that you are interested in inside these parentheses, and you will get the type. So let's execute all of these, and let's print out the point 1. Let's also print out the point that is 3-dimensional, and let's print out the point type. So what we will see in here is, well, exactly the one that I already showed you. So we have this point representation of this first object that we created with the coordinates 2.2 and 4.2. Then I printed out this 3D point. So as you can see from here, it has this kind of Z letter character in here describing that, okay, this geometry here is kind of 3-dimensional. So it has height or elevation information associated with it. And then the point type, so what is the type? We can see that, okay, this is coming from the class shapely geometry point. So it is kind of a point object that we have in here. So this is how quite simple thing how we can actually create points in Python. But of course, well, quite often we are more interested in how these geometries are related to each other and how we can actually start doing something with those geometric objects that we have, and how to extract certain information from them. Let's first see how we can actually get the coordinates out of this geometry that we now have. Typically, when you, for example, read something from a shape file or read something from some whatever spatial data format that you have the data in, you might want to have actually the information about the x coordinates and y coordinates for some purpose. That's quite a typical thing to do. So let's see how we can actually do that in Python. Now using these objects that we just created, of course, they are quite self-evident that we know those coordinates, but there might be cases when you don't actually know. And how we can get the coordinates is by calling, for example, now we have this point 1 that we created in here. So point 1 and pressing dot, and when I press dot and the tabulator, I can see all sorts of things that are available from here in a similar manner as when using the for example, pandas library. So from here we have an attribute called chords, and when I execute this and print the point chords, we should, well, we get a coordinate sequence. So the type of these coordinates here is that it is kind of a representation of those coordinates in this shapely package. And if we want to get the actual numbers out, we can basically call x and y. So by writing xy equals to point chords x and y, we can get this kind of information out. So first of all, what we did was that there is this chords attribute that is kind of a built-in
data type called coordinate sequence, and from that we can actually get the array of x and y coordinates in this way. We can also get directly, so if we would now, for example, want to have only the x coordinate from here, we could take x and y 0, and it basically gives you this, and then I think, is it like this, you can get the finally the x, but this can be a bit not the best way of doing it. So we can actually get the direct x coordinate directly from the point. So we have the point 1 in here that was looking like this. So if we call point 1.x, we can actually get this x coordinate directly, and the same thing of course is for the point 1 and y. So now we kind of have extracted those coordinates from these geometric objects. So typically, yes. What?
You had an initial with the array form, then you had D, 2.2.
Oh, you mean the this?
Yeah.
Now I'm not totally sure if I remember right, but it's related to the data type of these are basically NumPy arrays. So it's kind of ties the data type information into this. I will, but I'm not totally sure, or well, don't remember. I have taken a look at it a long time ago, but I think it's related to the data type of this array, because in NumPy you need to have, well, all the arrays are of certain type. They can be integers, they can be floating point numbers, and so on. So this is more or less related to that one. I will take a look at during the break, and I can come back to this one. Yes, good. But indeed, now we have seen how to create 3 different points, but let's see if we are interested in seeing what is the distance between these 2 points. That is already much more interesting thing to see and understand. So how can we actually calculate the point distance? Is that we can basically start using that we are interested in the distance from this point 1 into something else. So there is a function inside this point 1 when we use the dot and again tabulator. There is a function called distance. So by specifying point 1 dot distance and then in the square brackets, we can basically we need to specify distance to what. So from point 1 distance, for example, to point 2. So in this way we can basically calculate the distance between these 2 objects. So distance between the points is, let's do some magic in here. Okay. No, I will do it now. This. Point dist. So doing this, we can see that the distance between the points is more or less 29.72. Can anyone tell me what is the measure that we have here? Is this, what do we have in here? Is it meters? Is it decimals? Is it kilometers? What is it? Any ideas? Good. This silence is good because you don't know what it is. And it comes to the point of, if we don't specify the coordinate reference system to our data, we don't actually know what we have here as distance. If the numbers that we have specified here are decimal degrees, and we know that they are decimal degrees, then the distance would be in decimal degrees. If these would be kilometers or meters, then of course the distance would be meters. But now we can already see that actually specifying the projection for our data is really crucial, because without knowing that, the calculations that you do with the spatial data will be, well, whatever. So that's kind of the defining the projection is really crucial. We will see that, how to specify that in, I guess, next week. So we, in the Shapely, so typically you don't specify the coordinate reference system to each geometry separately. What you do is that you have a set of geometries and they all are in the same projection. So if you are familiar with shapefile file formats, there is this file called .brg, so projection. So that file is always associated with the shapefile that you have, and it has the information about what is the projection of all these data points or polygons or line strings or whatever the data we have. And that gives the information about, for example, is the distance now in meters or kilometers or decimal degrees, or how should those be calculated? Yes. Yes, good point. What this is a special formatting to print only 2 decimals of that number that we have. If we specify it, for example, 4, we will have 4 decimals. So this is kind of a string, a special string operator, this kind of percentage operator. If you Google Python percentage operator, I think here we have no, it's actually not that operator, it's string formatting. Yes, here is a bit of explanation, but it's kind of a special way of defining and automatically rounding, for example, the number. So what it does is that it basically rounds whatever the distance is in here is with 4 decimals. And with this special syntax, having the percentage sign and then the dot and then the number and F going to float, or I think, yes, float. So it is just how to round them up. If we want to have full numbers, you pass 0. But yeah, so that's basically what it is. This is quite useful whenever presenting, for example, when doing visualizations. So you don't typically want to have like 10 decimals in there, so you want to actually have them shorter. So this is a good trick how to do that. Good. So, yes.
And what about the purple percentage sign before the point is that?
Yeah. Oh yeah. I left this out. So how you actually use these percentage? I could actually show you another example. So this goes now into a bit of string formatting in Python. So, but there are two typical ways how you can actually, you can have, for example, some piece of text and then you want to kind of insert some numbers inside there depending on, for example, the calculation. So there are two different, the most typical ways is this kind of syntax using the percentage dot and then the number of decimals and F. The other one that is really typical is that you can pass some text information from some variable, for example. Text is let's now assume that the points are in decimal degrees. So you can basically use this kind of syntax to say that the distance is, it comes from here, it is rounded with 2 decimals, and then we have in some variable, like in this case this text, so we basically specify that okay, we have the format or the measures are in decimal degrees. So this percentage sign S, which stands for string, you can add whatever kind of text from variables inside this kind of sentence that you have, and you can repeat them as many times as you want, but there needs to be, so now we are inserting 3 different variables inside this sentence, and each one of these need to match with these variables in here on the right. So if we do now this, we will have distance between the points is 29.72 decimal degrees. And why do we have 2 times this decimal degrees is that because I specified 2 times this text, but of course this is not what I want to do. I want to have only 1, but if I do this and I have places for 3 different variables in here, so this is for the number, this is for the string, and then there is another place for another string. So if I now do just this, I will get an error, not enough arguments for format string. And this is quite typical error message when if playing around with these. So the reason was because there was a placeholder for 1 more variable in this sentence in here. So when I remove this, then it works okay. So this is a really short introduction to how to do these kind of things. There has been maybe a couple of examples in the GeoPython lesson, but we haven't really focused on these things. So these are good things to know, and hopefully you kind of now understand a bit how they work. Good. So now we just quickly went through how to create points and the idea of that you have inside these geometric objects you actually have different functionalities that you can already kind of do some calculations, such as the distance between the points. So let's continue with line string and take a look at a bit of how we can create that. So I will continue using the Cse Notebook and the Jupyter Lab. So creating a line string or a line is really similar kind of procedure as when creating point. So I import the line string again. I import it already, but this is kind of a similar thing. So from shapely.geometry import line string. We already did this when first importing all these point, line string and polygons, but I now do this again to just to remind how that is done. So with this line string object we can start creating lines. So there are different ways of creating lines or line strings from coordinates. So of course when you have a line you have at least two nodes and then the connecting line between those two nodes. So you can create a line string using point objects as input, and those objects should be inside a list. I think also a tuple might work, but let's create a variable called line, and here we use the line string object to present the line. And how we can create it is that indeed, as I mentioned, we need to pass a list of points that will be used to form the line. So these points are kind of the nodes that are connected to each other. And well, luckily we already have 3 points created in here. So let's pass these 3, point 1, point 2 and point 3 inside this line string. So here I have a list, and in here I can specify point 1, point 2 and point 3. And this is how we can create a line. Let's take a look. If I now just call this line, we should see that, okay, this is how it looks like if we would put it on a map. So it's this kind of V letter looking shape, and it works. When we print that line, we can see that the kind of GIS presentation or WKT presentation of this one is this line string, and then we have these coordinate pairs in here. So we have 3 nodes in this line string in here. Is everyone familiar what is a node? Yes. So we don't need to go that. So it's basically a point that connects different lines to each other. So now we saw that we can pass in point objects. So what this point 1, point 2, point 3 are, they were the points that were created before using the shapely point object. There is also another way, so it's not necessary to create those points beforehand. You can pass the coordinates as tuples inside the line string object. So create line string using coordinate tuples. So let's create a variable called line2, and again we use the line string object in here. What it needs to have is a list of coordinate or points. So now we pass in coordinate tuples, so 2.2, 4.2. So these are now the coordinates of the first point, and they should be actually exactly the same as that we passed in here. Then let's pass another coordinate sequence. So it's 7.2 minus 25.1. Oops, and there needs to be a comma in between. And then the third one is 9.26 and minus 2.456. So this way we can see that we have two identical, well, not identical because this don't have minus in front. Now we have two identical line strings in here, and there are two different ways of producing that line string. So either using the point objects that are created with Shapely, or passing in coordinates as numbers inside these coordinate tuples. Good, and we can see what is the type of this line 2, for example. We can see that it comes from the Shapely geometry module, and it's a linear string, line string object. Yes. As you probably guessed, there are also different attributes and functions that are available when using these line string objects. So now, for example, well, let's first see how to extract those coordinates from here. So exactly in a similar manner as with point, so get coordinates. So line xy equals to, well, we have the line and then dot, and down here we have the x and y, and when we print that out we should see that what we have in here now, sorry I forgot to check what this D means, but I will do that later, but we can see that now we have array of x coordinates and array of y coordinates. So here what is maybe good to understand is that all the x coordinates will be in one place and all the y coordinates will be one place, and the order of them is basically the kind of how the points are represented in here. But of course typically you want to extract only x and y coordinates. So let's see how we can do that. So extract x coordinates from a line. So let's create line x equals to, so we have the LXY variable created in here. So of course if we want to get the x coordinates, we can get them from this LXY variable and taking the first object in here, line x. So this way we can get the array of line x. We can take a look what is the data type of that. It's an array, as we can see. If I remember right, if we press line dot x, so if you have yes, so if you have more complicated geometric features than point, such as line, that is kind of formed out of many different points, for example, so there is no direct way of actually getting the x coordinates out of it. So if I press line.x, it says that the line string object has no attribute x. So this is a good thing to understand, but this is the way how we can actually get it. So we have the x and y coordinates having the both of them in here, so we can get by passing or getting the information from that. And if we really want to have the numbers, not the array, it's basically using this, passing the information from there. And now this is the first one, this would be the second one, and this would be the third one, coordinate from that list. But these are all of them at one go. And of course the line y coordinates are in a similar manner, so they are at index position 1. So line y, so now we can see that we have both of these in here. There are occasions when you need to understand the coordinates of lines, but it really depends on the field that you are working on. For example, I might need to understand what are the coordinates, for example the first or the last coordinate of a line when analyzing street network data and doing something related to intersections, for example. So it might be that I actually need to do these things, but it really depends what you are working on. Good, but of course the coordinates is just the raw information, but again, much more interesting stuff can be accessed by, for example, getting the what is the length of a line. So so how long, if we, for example, if we, for example, want to understand that we would have this kind of weird road somewhere, looking at this, and we would be interested in knowing how long is this this road. So it is really easy to get that information out of the Shapely object, and we can create a variable called line or L underscore length, and using the line that we are interested in, dot, and then we have the length variable somewhere in here called like this. So with one simple attribute we can actually get the length of that line string that we have. These are, how many of you have used ArcGIS like more or less regularly? Yes. I don't, are they now teaching quantum GIS in here, or what do they teach? Is it still ArcGIS? What did you learn when you went to GIS? Yeah, so it's still kind of ongoing process. Yeah. Okay, so then I discuss about ArcGIS. So this is basically, these kind of things are typically when you go to the attribute table and you create a new column and you calculate like the x coordinates and the lengths and the areas. So these kind of things. So actually what is happening under the hood in Esri products as well, most probably, is something like this. So you have those spatial features, and then you access the attributes like this kind of length information and so on. But indeed they are all kind of information that is directly tied into the object itself. What can also be useful often is that if you have a long line, well, for example in here, and you would like to understand what is the centroid point of that line. So where is the middle located? So we can also access that really easily. And let's take a look how that look, how we can do that. Get the centroid. So, and this similar approach applies to polygons as well, which is maybe the most typical thing to do. But let's create a variable called L-centroid. And again, there is line that we are interested in, and dot, and centroid is the attribute that we are interested in to access. So I print the centroid. So now we can see that the length is something like this, and the centroid position is located somewhere in here. But let's take a look, how do they really look like. So let's print out, not print, but have the line and the L centroid. No. So we can see, if we take a look at the attributes, that if we go and check the x coordinates of each of these tuples, the centroid is somewhere located in here. What I wanted to show is that in some IDEs it's possible to print out multiple objects on top of each other. But basically, where that centroid is actually located, so if we take a look at this shape, so you would basically assume that it's somewhere maybe along these lines. But what I assume what happens here is that the centroid is actually somewhere in the middle in here, because it's kind of how it's calculated, so it doesn't. This is now something that should be tested. Let's see if I open this one. Yeah, let's test it out so that we are sure what actually happens, but we'll continue on that a bit later. But I assume that it's somewhere, it's not maybe, doesn't follow this line, but it's somewhere in the middle. And what is actually good and worth noting about is that the type of the centroid, so if we print out the type, so what do we actually get out from here is that it's shapely point object. And this is quite good because you can directly start doing something with the point object, such as calculating distance between different centroids, for example. So there is no, it's not necessary for you to again like create the point object first from the coordinates, but it kind of nicely gives you the point directly from here.
Let's continue with the polygon information. So creating a polygon, as you might guess, follows exactly the same path. But now what we need to have when creating a polygon, so of course we need to have at least 3 nodes so that we can form a triangle. And how we can pass information inside a polygon object is that we need to have those coordinate tuples inside there. So again, let's import from shapely.geometry polygon, just to remind us that this is how we can access that. And let's create a polygon. So let's create a variable called poly, and how we create that is exactly the same thing as before. We can have polygon, and it needs to have a list of coordinate tuples as inside. So now this would be 2.2, 4.2. We are again using the same coordinates as before. This would be 7.2 minus 25.1, and the last one will be 9.26 minus 2.456. So this is how we basically create a polygon. You need to have at least 3 coordinate tuples in here, and that's how it's done. And we can see how it looks like. So now, based on the, well, when we compare this to the line that we had, so as you can see, it looks exactly the same, but now we have the connecting kind of line in here as well, and it created a polygon. So it automatically kind of ends or kind of puts the nose sequences together. Another way, so this is typically not the efficient way of doing, so that you actually type in the stuff on the coordinates. So let's create a polygon using the point objects. So because we already earlier defined 3 points in here, so of course we can use this information to actually form the polygon. So now these points will be the kind of corner points of that polygon. And how we can do that? Now, unfortunately, this is a bit trickier than when creating a line, because Polygon Object doesn't know how to take these point objects as list. So we need to do some list comprehension to do that, and we will probably spend a few times now with this. I will first write this down, and then we can discuss and see how confused you are. So first of all, what we have, oh, I started in here. So first of all, we have a list of points that we want to iterate over, and those are the point 1, point 2, and point 3. And these will be the corners of that polygon that we will create. What we need to do in here is that we actually need to iterate over each one of those points and take the x and y coordinates out of them. And of course, because we need to do all of this thing inside this polygon object, so inside these parentheses, so we cannot just create a for loop as we have learned to do. So we need to do it inside in here. So that's why we need to do this kind of list comprehension, and we basically do it by saying that for point in for p, which stands for point in this list of 3 points. And actually, when doing this kind of list comprehension, we are kind of, what we are creating here is a list of coordinate tuples. So this is the list of those 3 points, those x and y coordinates of these point 1, point 2, and point 3 will be inserted inside this list. And how do we do that is that we basically say that let's now do it exactly as in the materials. So for each point that we have in this list, give the x coordinate and give the y coordinate. So now what we actually have inside in here is that we have a for loop inside this creation of these of when creating this polygon. And for each of these points, so for P, we will get the x coordinate of that point and the y coordinate of that point and insert that inside this list. That will be inside another list. So this is confusing, I know, but let's see what happens when I call this. So now we get exactly the same looking polygon in here, but we need to do some special tricks for doing that. And the special trick is basically just creating this kind of loop that loops over each one of those points in here. Did you follow? Yes, so this is, I know this is really confusing. Let's take this part out of here. So let's now forget a moment that we want to create a polygon. Let's just focus on what happens in here. So what we actually have in here is that when I just executed this, is that we have a list of lists, and each of those lists have the coordinates of those points. So this is just a way of doing that in just one line, and what we are actually doing here is that we are creating a for loop based on those list values, so those 3 points that we have, and then from each of those points we are actually accessing the x coordinate and the y coordinate. And what we are doing in here is that we are actually passing those x and y coordinates inside these lists, but actually the even better way of doing this is that those should be not inside lists but inside tuples, so it follows the way that we actually learned before. So these are the coordinate tuples that we create using the point objects, and this is a list comprehension that is a kind of Python specific technique to actually iterate over a list inside here. So it is a complicated thing because we actually use some of the functionalities of those shapely point objects by getting the x and y coordinates, and then we at the same time create a for loop, and then when we have this in this format, then we can put it around or put the polygon around this. So when doing this, now we actually have a polygon. So this is what happens in here. Don't get worried about this because you don't need that often to actually do this in real time, or in real life. But this is basically how you can do it, and well, for sure there might be occasions when you actually want to do it. Yeah. Then let's take a look of the, so we have this polygon, shapely polygon object. So if we want to understand how to use this polygon, we can call help and press the polygon, or put the polygon object inside this help parenthesis. So in here we have a documentation about how this polygon works. So from here we can see few things. Well, first of all, that that the polygon is a two-dimensional figure bounded by a linear ring. It has non-zero area. It may have one or more negative space holes, which are also bounded by linear rings. So basically, if we think about a polygon, we have the outer ring or the exterior of the polygon. So basically how we define where it goes, and then we might have holes inside. For example, if you think about that we want to present with that polygon a land area, and then we have some lakes, for example, inside that land area, and we want to kind of take that away because, well, they are not accessible by foot, for example. So how do we actually present those lakes is that we need to make holes inside the polygon. So basically the polygon object takes the exterior as a list of, well, as polygon as we learned now in this way, and then it has the interiors defined, and they need to be inside the polygon exterior. So there's a lot of documentation in here, but let's now see how we can create a polygon with the hole, so that you can actually see how it's done. So what we will do is that we will create a boundaries of the world using the decimal degrees as the exterior, and then we will create a hole inside the world in a way that you will soon see. So let's create a bounding box for the world. Well, it's not a bounding box, it's exterior. So world exterior equals to, and now in a similar manner as before, so how do we create a polygon is that we need to specify the corner coordinates. So when we think about the world and how it's what are the bounds of it, so we have minus 180 as the x coordinate, and if we put 180 and 90, we have basically the upper left corner of the world. Then we have the lower left, which would be minus 180 and minus 90, and then we would have the lower right corner, which would be 180 plus minus 90, and then the upper right corner of the world, which would be plus 180 plus 90. So this is kind of what we need to have to form the boundaries of the world, and we can take a look how it looks like. So world equals to polygon, and we say that world exterior is like that, and then we just call world, and well, we just have this kind of box, and you need to use your imagination to think that this is a world. But basically these are coordinates representing each corner of the world using the latitude and longitude information. But now what I wanted to show is that let's create a hole so that we kind of rip out the inner parts of the world and have only 10 decimal degree kind of boundaries. So it will look like a painting, and the kind of, well, there will be a hole inside. So let's create a hole. Not hole, but hole. So now we will rip off 10 decimal degrees from these values. So let's say that hole, and a similar manner as before. So now the difference is that, of course, if you think about polygon, you might have multiple holes in it, not only one. So actually how the polygon wants the coordinates is a list of polygons, so that each list inside this list presents one hole. We will now do only one, but this is how it is done. And let's create another polygon, now just presenting the same things but taking then 10 decimal degrees off these ones. So I can actually copy and paste this information here and put it in here, and now I just change these values so that this will be minus 170, this will be 80, 170 minus 80, 170, 80. So now we have kind of taken 10 decimal degrees off our world, and this will be the hole. So how do we actually now assign that hole inside in here? Is that we basically specify world with a hole. So how we can do that is that we want to specify what is the shell of that polygon, and the shell is, well, it's the ulterior ring or the exterior ring. So we specify this, that this world exterior that we specified in here is the shell of the polygon, and then there is a parameter called holes, and we specify that the parameter or the variable hole is this one. And when we do that, and let's call it, we should see that this is what happens. So what we did was that we created boundaries of the world. We created a large hole inside because we only left like 10 decimal degrees on the outer boundaries of the world bounds, and this is what we will get out. Let's take how does it look like when we print it out. So now this is the kind of text representation of the polygon. So we can see that we basically have two different set of information here. So this is first the shell of the polygon, and this is the hole inside that polygon. So this is kind of a special thing when thinking of the polygons and how we can create those things. Does it seem more or less clear? It's fairly trivial thing, but this is something that you need to understand, because when you start working with polygon data and start manipulating it, you need to understand that these the geometries are formed in this way, and there can be holes inside a polygon. Good, but then again, more fun stuff is that when we start using the different functionalities and get different information from that polygon. So we can, for example, if thinking of what we were able to do with line strings, we were able to calculate the length. So when we have polygon information, we can calculate, for example, the length of the exterior. We can calculate the area. We can see what is the bounding box of that polygon. Of course, now when we basically have this kind of rectangle, bounding box doesn't maybe make that much sense, but if you have a rounding or somehow different looking polygon, knowing where the bounds are might be useful, and so on. So let's take a quick round of the different functionalities of the polygon. So of course we can get the centroid. This is something that I do very often. So if you have, I don't know, for some reason understanding where a centroid of a polygon is something that you need every now and then. So that is easily accessible by us, for us. So we can say that world centroid equals to, well, world centroid. So this is exactly the same attribute that we used before, and we can get it with that attribute. And well, of course, when thinking of the world and where is the centroid of the world, for some reason it's -0, but well, it's located at 0, 0. Then bounding box. Does everyone understand what is a bounding box? No. Good. Bounding box. If you think about that, you would have, well, if you think about this polygon in here, so what bounds or bounding box basically gives is that it gives it tries to fit a rectangle on top of that shape that you have. So basically, if we would draw a bounding box in here, it would see what is the topmost location of that polygon, and it would draw a line somewhere in here. Then it would take the leftmost bound of location of that shape, and it would draw it in here, and similar like the lower and the east. So it will kind of try to fit minimal rectangle on top of the feature that you have. So that's basically a bounding box. So it kind of gives you the area of where the shape is somehow operating. So that's a bounding box, and we can get the bounding box really easily. We can create a variable called world box equals to world dot, and here we have a list. We have bounds, and this is how we can get it. And well, surprise, surprise, if we think about the world, what we have in here is that we have the bottom left corner of the world and the upper right corner of the world. So we have the minimum x and minimum y coordinate, we have the maximum x and maximum y coordinate. So basically, when defining a bounding box, you only need to know two corners of the rectangle to be able to define it. So that's why we have this information in here. Then the exterior can be getting easily. So we can create world ext as exterior, and again we can world dot exterior is the one that we want to use here. We can print it out to again see what do we have. As we can see from here, we have linear ring as the exterior. So it is a kind of line that is connected from one point, starting from a node and coming back to the same node when done in the full circle. If we want to understand what is the length of the world. Yes?
So we should think of that as a circle, you said? The linear...
Yes, well, it's not a circle per se, but it's some kind of polygon, well, not the polygon feature, it's some kind of line that is starting from one point and it goes where it goes and it comes back to the exactly to the same node. So it kind of makes a circle in a way.
But in this case it's a rectangle, right?
Yeah, in this case it's a rectangle, that's right, yeah. As we can see from the coordinates, these are the kind of, these are the exactly the same node coordinates that we use for defining the world. Yes, and if we want to know what is the length, if we would walk each corner of the world and go like this, so how long should we actually walk? So we can of course get the length of the exterior, and that can be done. Length. So we can use this exterior information in here and get the length of that. I can show you soon another way. So now we can see that if we would walk like this, we should walk more or less 1080 decimal degrees, and 1 decimal degree is, I don't remember correctly, 1 decimal degree equals to 111.32 kilometers, more or less, depending a bit where we are. But let's see, times this. So if we want to take a short walk, it would be 120,000 kilometers if we would like to walk from each corner to every another one, assuming that we would be able to walk on top of the sea. Great. Cool. So this is now we basically use this variable here to get the length, but of course we can, if we are interested about the exterior length, you can chain these commands together. You don't need to follow, but we have the world, that is the polygon that we have, then we have the exterior, and from that exterior we can have the length. So you don't need to have this kind of step. You can, like we did in here, that we first stored the exterior information into this variable, but you can just directly chain these word.exterior.length and you will get the same answer. Good. Let's see, do we still have something fun in here? Actually, something we haven't yet checked, but maybe we could as a final things. Let's go back, for example, when we created the line. What is quite typical when doing GIS things is that you can have, for example, some kind of road, and then you want to understand certain kind of, like, within 50 meters from that road, the area is more or less you wouldn't like to grow your potatoes there. So you want to create a buffer around those roads and understand the unsuitable areas for farming, for example. So this can be done really easily using the Shapely functions. So we have the line in here, and if we kind of take a look of the functionalities that we have in here, so surprise, surprise, we have this function called buffer, and doing and saying that line.buffer, and again shift plus tabulator, I can get the documentation from this function. We can say that okay, this has parameters distance, resolution, quad sex, cap style, join style, meter limits. I don't even know what all these things mean. Probably there is some information somewhere, but what I'm mostly interested in that okay, these are typically something default values, but there's this distance. So how big of a buffer do I want to make from that line? So now we have decimal degrees in here as the starting point, so probably if I want to make some small buffer, I would like to use something really small, like let's make more or less 10-meter buffer around that. So I should do and use something like this 0.0001. So that's how I could more or less create 11-meter buffer around. So by doing this, what happens is that it will create, now this thing changed its color. It looks more or less the same. Let's make a fat one. Let's make it even fatter. Now it starts to look a bit different. Let's make it even more like this. Now we start seeing something. But now, as you can see, it starts to create really a buffer around the feature. And when we let's store this into buffer, and let's print the buffer. So now, as you can see, well, of course, when thinking about what buffer does is that it will kind of grow the feature and do the buffer around. So what is actually the data type of that, or what is the geometric object type? So it's a polygon, of course. So then we can, for example, see that what is the area of that buffer and so on. But yeah, this buffer analysis is really typical in GIS, and we can basically do that directly by using this .buffer function that is part of, it's built into each one of these geometries. So that's good to understand. Let's see, do we still have something more fun in here? Convex hull, discharge, yeah, they're simplified. Yes, that is something that we will do later. Yeah, maybe this is enough for now, but basically, hopefully you have now gotten a short introduction about how we can create different geometric objects in Python. This is probably the most boring step of this course, so hang on. And but you need to understand, because these things are under the hood on everything what we are doing and starting to do from now on. There is some optional information about the collections of these geometries. What it means is that instead of having a point object, you can have and store multiple points. So if you think about attribute table in ArcGIS, when you click one row, instead of actually showing and kind of painting one point from the map, it will have multiple points. This is what happens. So you kind of on single feature you have multiple objects inside, and the same thing with the lines and the polygons. So that's what we have. You can take a look of the materials if you're interested in. Maybe one kind of key thing to understand is that when creating these multi-points or multi-line strings, you create them exactly the same as when creating lines. So multi-line, well, the word multi kind of says it all. So if you create a multi-line string, so you have line strings but multiple of them, so then you can kind of create these kind of things. But the difference is that if you, for example, calculate the distance of those lines, it will be the kind of sum of all of those lines. If you calculate the area of multiple polygons, it will be the sum of every polygon that is stored in here. So, for example, in here, in this case.
Will it double count overlaps?
That's a good question. That's a good question. Let's go and see if the documentation tells us something. So there is the Shapely user manual. Well, and by the way, this is actually good that you asked. So in the materials, so when we have the motivation for the course, and in down here we have the list of these. So each one of these packages have their own documentation, and there are links to those. So for example, if we are interested in, let's say, like this. So there are links to the kind of documentation of what you can do with that package and so on. So it's good to maybe take a look of these links if you're interested in. And of course you have the materials that I have written there, but there might be questions that I for some reason haven't write down. So it might be good every now and then to actually go and dive and check the actual documentation of these libraries. So now we are interested in understanding what happens if we calculate or do the collection of polygons and then see if we do, if we calculate the area, so if they overlap, what happens? Yeah, well, I will take a look at that later. Now I don't find immediate answer to that one. Yes, but I will post that to Slack if I find the answer. Do you have any other questions at this point? Does it seem more or less understandable? Now we are talking much about objects, and that's what they are. We haven't really discussed anything about object-oriented programming, which is basically what these objects are. So they are classes that has attributes and functions. You don't need to worry about that so much at the moment. Object-oriented programming is really beneficial and good, but for doing data analysis, typically that's not used that much. Well, it is used, but not for example, I don't use it that often. Yeah, but if you don't have any immediate questions, we could take a quick look of the exercise for this week. The actual GitHub Classroom will be updated later once we get. At the moment, we don't yet have the private repository, so I didn't want to put them out yet because, well, it could be done, but everyone would be able to see your answers, and I don't want to do that. So it should be hopefully up and running soon. But there is the open copy of that exercise available. So if you're interested in looking what the exercise looks like, so you can click on this link, and there will be the exercise already here. So for this week we will have 4 different problems. We can take a look at them. So problems 1 and 2 are together, and problems 3 and 4 are together. And what we will do is that we will exactly practice on creating these geometries. We will practice on creating functions so that you kind of can practice what you learned already during the GeoPython part of the course. You will also practice a bit of using assertions to kind of, when using functions, it's kind of important to make sure that the function that you have created is used appropriately. And for example, incorrect values are not passed. So if you are summing, for example, 2 values, 2 numbers, so that the function takes care that text, for example, is not inserted there. So this assert functionality is really good. There is hints for this week. This one. Okay, I need to fix that link. Here are hints. So there is hints about the assert statements and how you can use that. And then there is a hint about iterating multiple lists simultaneously that you will need. I will tell you more. But the idea is that you will create functions that can be used to create different kind of geometries. So you have function for creating points, really simple thing, kind of that it takes x and y coordinates, and then it creates a point and returns that point to the user. So that's kind of maybe a bit trivial thing to do. But then like how to create a polygon, how to create a line geometry. So those are a bit more complex things. So it might be good to have a function to actually, okay, take these coordinate tuples or points and create me a line. So you can practice the use of functions and so on. And these have been written in a way that you will repeat the things. So for example, when doing the first one and you first do the assert function and try to get it working, so you will repeat it many times so that you will get used to and hopefully start to understand how they work. The second problem is practicing exactly how to get, for example, area of a polygon, how to get centroid and how to package that into a function. So you should be able to do it easily by following the materials for this week and then just applying that so that you actually create a function and do that. So that's the only maybe difference compared to the lesson materials. Then the exercises 3 and 4 is more kind of a data analysis approach. So we have some data that you want to read in, and in this case, quite typical situation is that you have a file, such as text file. In our file we have something like approximately 15,000 rows, and each row contains information about coordinates. So this is this kind of OD data, so origin destination data, from the travel time matrix that we used quite a bit in the research lab. So you have X and Y coordinates, or Y and X coordinates, and the idea is that you would read this data file in using pandas. You have already seen how to do that, and then you should use this coordinate information from that file. First create points out of them and assign them into lists, and then finally, because these origin destination points are basically they can be represented as lines representing movement from point to another. So the last problem is to practice how to actually use those points and create line strings out of them, iterating over the data frame and so on. So as you can see, we are going to repeat and practice the things that we learned last period and kind of continuously come back to those. Good, but that's it. So this is the kind of introduction to geometric objects, and next week, as said, so we will start using the GeoPandas and start really diving into the spatial analysis using a bit more kind of handier tools. Any questions still? So Vuokko, now as you came, so we decided, as the practical session is on Thursdays, so that they have time until Wednesday, because it's, yeah. Yes, yeah. So that's kind of the schedule. Yes, yeah, we did, but actually there are some now still when you're here. So there are some. This actually needs to be updated. So it was this 12th of November, right? So this will actually be on the Wednesday. So we have a couple of exceptions. So not next week, but week after that. So the lecture won't be at this day. It will be on Wednesday, because we have some overlapping things. Yeah, so the contents are more or less the same as last year, so there are already, or there will be the videos like immediately available from last year that you can look over. But yeah, the lesson will be here. Next Monday might be that we start earlier. I still need to check. I might need to be at Paikkatietomarkkinat, so if I manage to change the schedule, so we might have it earlier in the morning, the lecture. But let's see, I will notify about that in Slack and send email as well when I know for sure.
Independence Day, of course, there's no class on the 6th of December. That's a Thursday, so it would be kind of one of the practical sessions.
That's right. Yeah, on the last, so indeed, yeah, the practical session will be eaten from this work. We will just, yeah, have the practical session then on the next week, or somehow extend the deadline at least. The last, so the class 7, so there won't be any exercise at all with the QGIS thing. so you can then use the time to work on the previous exercises and start working on the final assignment that we will introduce you probably during the class 6 already, so in the early December. But that's it for today. So on Thursday we have the practical session, and you can come there to get some help.